A review of head injury metrics for computational modeling of brain strain. 1.5 million traumatic brain injuries occur in America yearly, resulting in permanent brain damage and impairment. Identifying ways to limit and mitigate the negative effects of TBIs is essential to effective patient care. Current metrics are shown in Figure 1, with kinematic and strain metrics and computational models being the primary methods to quantify brain damage. We compiled a literature review of different papers quantifying traumatic brain injuries, prompting questions for future research avenues.
Kinematic metrics are commonly utilized as brain injury predictors and indicators of head impact exposure. Research beginning in the 1940s investigated differences between rotational and translational kinematics. Using a gelatin model of the brain, Halborn found that greater strains occurred under rotational motion and concluded that sudden head rotation is one of the main causes of injury. Moving further, researchers at Wayne State developed a tolerance curve for human tolerance to brain injury based on linear acceleration. GAD severity index is a continuation of tolerance curves and is used to approximate injury risk. Shortly after, head injury criterion was developed as a time-based metric that spans the duration of a head impact. Brain injury criterion and universal brain injury criterion are two of the newest metrics used to compute brain strain at levels similar to an FE model.
Okay, focusing on strain-based metrics. Let's say we are modeling impact in two different directions, two different angles. We're simulating that brain strain, and we're going to produce two different strain mappings. It's important to think about this because kinematic metrics don't account for regional distributions and properties based on impact location. However, with strain-based metrics that quantify tissue deformations using region-specific properties allow for spatial and directional distributions of strain measures throughout the brain. So focusing on metrics that are used in strain-based research, we range from maximum principal strain to strain rate to the product of these two to cumulative strain damage measure, with MPS and CSDM most commonly being reported together. Novel metrics range from maximum shear strain, which is shown to better correlate with sensitivity analysis and comparison of experimental findings from cortical damage, to volumetric strain and shear strain metrics, which were developed from the CSDM curve and outputted more accurate strain distributions over the whole volume of the brain. We can see this in direct use here. The top row shows experimentation that relied on acceleration profiles only to model brain strain, and the bottom row uses axonal strain as a strain metric, producing higher resolution strain distributions and better injury prediction.
Moving on to computational models. Several FE head models have been developed to various degrees of accuracy and complexity, such as the UCD brain trauma model shown here. These FE models have been used to validate strain metrics, calculating global MPS, or 95th percentile strain in brains. Emerging research simplifies the conversion from experimental loading conditions and output MPS using machine learning. These models compare rotational velocity and acceleration to create a 2D training set, preserving impact information in the brain using multiple variables. There are many more input metrics yet to be tested in these models and room for increased complexity. ML models are less resource-heavy than FE brain simulation and are a promising future for computationally efficient TBI research.
By reviewing the literature, it's easy to see that there have been tremendous strides in the field. With this new information, better development in the automotive and sports industries are made, all allowing for better protection of people at risk for traumatic brain injuries.